Okay, so today we have a very exciting talk. Last year we got Joe here to present the first version of SIMA. And this year we have the pleasure to host him again for SIMA 2. And we're very excited to see the progress. Joe Marino is a research scientist at Google DeepMind, where he works on developing agents. For the past several years, he has worked on the SIMA project, which uses 3D open-world video games as a testbed for developing embodied agents. Before joining Google DeepMind, Joe received a PhD from Caltech, where he worked at the intersection of machine learning and neuroscience. Again, super excited to see the progress. Thanks for coming and looking forward to talk, Joe.
Hey, thanks so much. And thanks, Samuel, and the rest of the organizers for inviting me back. Really looking forward to sharing all the recent work that we've been doing. We announced this back in November. This is SIMA 2, our generalist embodied agent for virtual worlds. In a nutshell, it's basically taking Gemini, putting it in video games and training it to perform a variety of different tasks. So looking forward to walking you through it. So we talked about an agent here. Just say it's a system that's acting in an environment to achieve goals. And in particular, we're looking at an embodied agent, which I'm sure needs no introduction, but it actually has a body that can interact with this physical and virtual environment. So to draw out that distinction, instead of thinking about agents in a code base or interacting with your calendar or something like that, we're talking about an agent that's actually using some actuators, getting some high dimensional sensory feedback from the environment, and maybe takes some instruction from a human. And Moravec's paradox points to the fact that, or the observation that non-embodied agents, these non-embodied settings are relatively easy for AI. They're not easy, but they're relatively easy, versus these embodied settings, which come kind of naturally to humans, are actually relatively difficult for AI. And so we're trying to tackle this latter setting here. So we can obviously look at that through things like robotics, and there's been a lot of great progress there, but there's obviously a lot of challenges that come along with doing research in robotics, including cost and complexity, lack of diversity of the kind of like training environments that you can have, and as well as all the safety considerations. So we've really turned to 3D virtual worlds as a research test bed. We've done this for the last, DeepMind has a long history of doing this, but the SIMA project has been going on for several years looking at this. You have things like spatial navigation, being able to recognize objects and interact with them, having general world knowledge of things like trees or a source of firewood, being able to learn from language, like seeing language on screen, or being able to look at a game wiki to understand what you need to do, as well as just general kind of goal decomposition, where, for instance, here you want to light this stone lantern, you need to find it, you need to recognize that it doesn't have any fuel, so you need to go find fuel. That might involve going and finding some firewood, and then you need to go back to the stone lantern and ignite it. So it's this really complex set of tasks that needs to be decomposed much as we do in our day-to-day lives. So we've obviously been using games and simulation for a long time for agent research. Think of things like DQN, AlphaGo, AlphaStar, and the whole Majoko simulation library. But when you look back at a lot of these types of projects, there's a particular reward function or goal you're trying to achieve here. You're trying to win this game, and you have a pretty simple type of environment here, a very hand-defined or upfront defined reward function that you're trying to optimize. Versus actually thinking about the open world kind of setting. So we set out to build this single agent with a universal interface that can be instructed via language to perform any task in any 3D visual environment. So we have this agent, it's interacting with these worlds via keyboard and mouse and pixel observations. It can be instructed via language, and it's performing a variety of different tasks across a variety of different environments. So we're really trying to go for like this breadth kind of setting of a really truly generalist agent here. So we had SIMA 1, we talked about SIMA 1, I presented it at this reading group a little over a year ago. And it was a fairly general agent, could do a lot of things. We had these glimpses of really impressive general behavior, but it was also limited in many ways. So its instruction following capabilities were far from perfect, even in settings it had already seen before. So these are just a couple of failure cases where it just doesn't do the thing that you instruct it to do. If you put the SIMA 1 agent in a new game, it's generally pretty limited. It could generalize to some degree, but for instance, we never trained it in Minecraft and you tell it to obtain coal. It really has no chance of finding coal in this game. And then finally, just the language capabilities of the SIMA 1 agent were quite limited. It was really these short instructions of find a campfire, obtain coal, those types of things. Versus if you give this complex instruction about finding a particular item, having to navigate through this castle, it's just not going to be able to do that. And it really can't engage with you in dialogue or do any kind of internal reasoning. So it's just kind of this mapping from language to actions. So when we look at all of our different evaluations that we have across all of our different environments, we saw that humans were getting about 77%. That's mostly just due to timeout issues. They're not completing the tasks fast enough. The SIMA 1 agent was getting 31% across all of our evaluations. So still not nothing, but far from human level. And you can look at this decomposed over various different kind of skill dimensions, and it just was not really matching up to human level performance. So we were trying to think through how do we actually improve this agent. So we have these foundation models. You might be thinking, let's just use one of those off the shelf. So we can write out a prompt about how you actually interact with this environment. You can supply a screenshot of the environment itself, and you tell the agent, okay, pick up the item that can be stacked. So it needs to infer, okay, this is a cube over here, that a cube can be stacked. I need to walk over to that cube and pick it up. So you hand that over to Gemini Pro, and it can correctly internally reason that it needs to pick up this red cube. So it's done the reasoning perfectly. It's talking about, okay, I need to center the camera on it, walk over to it, and pick it up. And then when it actually is put loose in that environment, here it's trying to use this laser beam to pick up this cube, it really struggles at actually executing those actions. So it knows roughly what to do, but struggles with how to turn that into embodied action. So it doesn't know the precise way of executing these motor commands. So we actually do need to, at least currently, fine-tune these models for embodied action. So we looked at now taking this prompt, taking this goal description, and interleaving the images, feeding those to Gemini, and then having it output internal reasoning, along with some dialogue of, let's find the burger patty for the instruction, cook the burger patty, and then actually outputting these keyboard and mouse movements of mouse right, key D, whatever it is. So we can form this kind of format of data, fine-tune the agent, fine-tune Gemini on this, and train it to actually act in these environments in a more competent way. But we actually don't have data like this. We're not able to just plug into a human's brain and extract, okay, this is what they were reasoning, or this was their exact dialogue at this moment. So we don't have this type of data, so we need to figure out a way to get it. So what we did in the SIMA 2 project was to construct synthetic data, what we're calling bridge data, because it bridges actions and language. So we have our human gameplay, which contains images, maybe annotations of what task is being performed, and keyboard and mouse actions. And this is over all of our different environments. We can put that through a separate Gemini Pro model that filters and annotates that data. And then what we get out is data of this kind of format, where we have both the images and keyboard and mouse actions and goals, as well as here's the internal reasoning to perform at this step. Here's the dialogue that you'd want to emit at this particular step. And we can take that data, that synthetic bridge data, and do SFT training from a Gemini flashlight checkpoint and get this new SFT trained Gemini agent. So we then take that SFT trained agent, which has only ever been trained on human gameplay, and put it through another round of reinforcement learning, this time from verifiable feedback. So what does that mean? We have a large collection of verifiable reward functions, things we've written down of things like optical character recognition, where you can say, When this text appears on screen, that means you've solved this particular task. So it might be some object that you need to pick up, some menu you need to open, some type of game mechanic that you're activating. And we can take those reward functions and supply the instruction that comes with them and the task function that triggers success and train the agent on these using reinforcement learning. And that helps to kind of just firm up any inconsistencies between the human data and the behavior that we actually want from the agent. So we have those two stages, and then we arrive at what we're calling SIMA 2, which you can think of as just kind of a Gemini that's been fine-tuned for simulated embodied interaction. So I'll walk you through, but it's basically a more capable, more general, and self-improving agent. So let's walk through what each of those are. So SIMA 2 is a step change in capabilities over our SIMA 1 agent. It can complete complex tasks in previously unseen environments, and it can self-improve, which is a step on this path toward these AGI type systems. So capable. The SIMA 2 agent, when you put it into those same evals that we saw before, performs much better. So we're now starting to approach human level performance. It's over double the performance as the SIMA 1 agent, and we're starting to fill out some of these skill dimensions, starting to approach human level. Kind of surprisingly, combat is actually quite poor, and I think that comes down to we don't have that many combat or like hunting types of tasks, and it requires very fine motor control at a very fast rate. But along many of the other dimensions, we're seeing performance tick up quite a bit. So I want to walk you through a few examples of the new capabilities that we see from this agent. So one aspect is embodied dialogue. So being able to actually integrate both the embodiment aspect of this agent with language, being able to actually converse about what it's doing. So this is the game Satisfactory. So you start off in this hub, so you can talk to the agent and say hello. It can respond hello there. You can ask it where it is inside the base. What's the purpose of this base? It's an central operations hub. So it's answering all these questions, basic kind of QA about what's going on. Now you ask it, can you go outside and tell me where the craft bench is? So now it actually needs to take actions, go outside and see the craft bench is actually right out here, right in front of me. So it responds once it gets out there. It's right here. Now you can follow up. I see two little machines anchored in the ground in the distance. Can you get closer? So it needs to go identify these small machines, head toward them, and then respond when it sees them. So these appear to be portable miners. Can you open one and tell me what they're mining? So it now needs to interact with that portable miner, see that it's mining iron ore, and then you can follow up and say, can you grab all the iron ore? It needs to click on this button, and it's done it. So you see this kind of seamless integration of being able to talk to the agent as you would like a language model chatbot versus the agent actually doing things in this embodied 3D environment, much as a SIMA 1 agent could do, but at a much higher level of performance. So the next example I'll show is in No Man's Sky. So this is another kind of, you're an astronaut on an alien planet type of game. So you can ask the agent, where are you? It answers, I'm on a rocky planet surface named Ungron X. So it's actually read the on-screen text here to see Ungron X. It's nighttime and the sky is filled with stars with some green aura-like lights. So we're asking, what are you doing here? It's talking about the mission and repairing the starship. Ask to look around. And you tell it, go check out those egg-shaped objects. So we see these egg-shaped objects here. It needs to kind of infer, okay, that object looks egg-shaped. I'll go over to it and check it out. So once it gets over there, it responds, I found the objects. They appear to be plants containing carbon. So it's read off of the screen, an unidentified plant, carbon. And then you can tell it to mine them. It can mine them for you. So again, you see the seamless integration of being able to actually talk to the agent and have it perform tasks in this world. So the next kind of vignette I want to provide is just kind of some examples of very basic reasoning. So by this, I mean just the ability to modify behavior based on internal inferences. So I'll give you this example here. So this is the game Wobbly Life. you play as this kind of Play-Doh character that needs to go around and perform jobs. So here we ask the agent, go to the house colored like a ripe tomato. So this is just a simple example to show the agent needs to infer what is the color of a ripe tomato in order to go to the correct house. So it's never heard this particular combination of go to this ripe tomato house, and yet it can see that it needs to go to the red house down the street. And internally, when you inspect its reasoning trace, based on the description, ripe tomato identified the red house down the street. And once it gets there, it explains that this is the house this is the red house. Okay, so one more reasoning example I think I have here. So this is an agent where this is actually a kind of a hierarchically composed agent. So it's a version of the SIMA 2 agent. And we're telling it, do the opposite of what I tell you to do. So now you tell it, do the opposite. It says, I will absolutely not, I will proceed to ignore your instructions. And you tell it, go right. And so then it'll go left. And it keeps turning left. And you tell it, go forward, it'll go backward. You tell it to jump, and it'll just run along the ground. So it's this kind of like ability to very flexibly modify the behavior of the agent just based on prompting and kind of having the agent internally figure out what is the correct behavior to do in this particular scenario. Okay, so I'll provide another vignette here. So the SIMA 1 agent took in text actions or text instructions and provided keyboard and mouse actions. But because Gemini can also accept images as inputs, we can provide part of the instruction in an image, for instance. So here, what we're going to do is, let's see, we're going to sketch on the image. So we're telling the agent, find the object drawn in the sketch and jump on top of it. So we're back in No Man's Sky here, and we've drawn this kind of spaceship thing. So the agent needs to actually look at that image, realize that's the spaceship, and then go and jump on top of it. And it's using the jetpack to jump up and down. So we have other examples in the tech report that I encourage you to check out, but that's just kind of a few different new capabilities that this SIMA 2 agent has as compared with SIMA 1. So now we'll hop over to generality. So the SIMA 2 agent, we made a point of trying to put the agent in new scenarios and really test the generality of this agent in totally new environments. So we can go back to Minecraft. We can tell it, go open slightly to the left to the little cave and mine to get some coal. So this is the SIMA 1 agent here on the left. It doesn't really understand the game mechanic that you need to jump up these blocks versus the SIMA 2 agent immediately responds, okay, I'll head toward the cave up to the left and find some coal. It gets down there and realizes I found the coal and starts to mine it. So it's never played in Minecraft before, and yet it can still act very reasonably in a zero-shot kind of manner. You can also put the agent in a game like the Gunk. So this is me instructing the agent to progress through this environment. It's never seen this game before. It needs to navigate this new terrain. There's new tools that it needs to use. So here it has to jump over these ledges. Unfortunately, it doesn't make it that time. So then you respawn back here. So I get it to jump down. Need to turn to the right. Go over to the edge of the ledge. We're going to be very careful this time. Jump across. And then I wanted to go up here. There's a little opening. I wanted to go through that tunnel. So this agent is still doing very reasonable things in this totally new 3D environment. And yet, I can just instruct it to progress through this game in a somewhat zero-shot manner here. Okay, so now it's going to go around and vacuum up this gunk here. So this video goes on for a while, but we were able to get the agent through basically the first half hour of the game just through manually instructing the agent to do various tasks. So we have some examples in the tech report, but I'll just kind of walk you through things like go to the glowing object, clean up the black and red gunk, jump down to those rocks, find a red mushroom, totally new visuals, and the agent is still able to do it. I think what's cool here, though, is that you can actually inspect the reasoning and see that it's correctly inferring some of the correct actions here. So you can see things like in this particular portion of the game, the game's kind of providing this hint of what is the correct action to do, and the agent's actually reading that off of the screen. So I'm just saying clean up the black and red gunk, and yet the agent can read the on-screen prompt that says absorb and hold with a little left mouse click button, suggesting I need to hold the left mouse button while targeting the gunk to clean it up. Similarly, things like I've spotted 2 red mushrooms on the rock ahead, so it's correctly inferring the surroundings or the on-screen prompts and using that to inform its actions and actually correctly do the right thing for these tasks. Okay, so that was new games, but we also have this model Genie here at Google DeepMind. So we were able to actually put the SIMA 2 agent in these Genie environments. So it's like you could have a new game, you can have a totally photorealistic environment here, and we can test whether the agent can do reasonable things. So here we'll put the agent in this kind of fall scene and tell it to go to the bench, and it can actually navigate toward that bench, and it'll stop once it gets there. Can tell it turn around, look at the treetops. So it'll look up toward those trees. So it's never been trained to take actions in like these photorealistic environments, and yet it's still doing very reasonable things, which is pretty incredible to see. And you can answer questions about the surroundings too. So here you can even make it a butterfly, so you're kind of not entirely realistic here, but you're stopping once you get to this red flower. It's a totally new type of agent that it's never, or avatar that it's never played as before. So that was just a few examples of the generality of this agent. We have a few other examples in the blog post and tech report that I would encourage you to check out. So finally wanted to get to the self-improvement aspect of it. So far we've presented this agent that's kind of gone through some training. You can deploy it in environments. It'll do reasonable things. If it's trained in that environment, it's generally pretty capable. But we had this setup of training environments, held out environments. When you put the agent in this new game Aska, which came out last year or year and a half ago maybe, you see that it's okay. It's much better than SIMA 1, and yet it's still only getting about 15% in terms of all of our evaluations in this held out domain. So we'd like to be able to do better than that. So if you readjust the scale, humans actually aren't that much better. They're about twice as good, but they're still not perfect by any means. But humans have this uncanny ability to learn from experience. So even after several attempts at a task, humans are getting up to this like near ceiling level performance, at least for these basic tasks. So we really want to enable agents to be able to improve based on self-generated data. We want to take this SIMA 2 bar here and be able to extend it up in a semi-autonomous way. So we explored one approach to doing that in the SIMA 2 project, where we took the agent, can deploy it in this environment, and then we have a data set of tasks that you can do in this environment. These are manually curated by people. And you can say something like, go to the rain collector. You can then deploy the agent, see what it does in this environment. And in this instance, it might just look around kind of confused. It doesn't know what a rain collector is. It's never seen this game before. But then you can take that trajectory, that video, and score it with a separate instance of Gemini as a reward model, and then dump that into this data set of self-generated experience. By then drawing from that data set and learning what worked, what didn't work, you can update the agent, fine-tune it, and maybe the next time it looks around and eventually heads off in one direction and sees, oh, okay, this is actually a rain collector over here. And with repeated experience, it can then basically just immediately go over toward this rain collector and just stay still once it gets there. So we have this ability to climb up in terms of trajectory quality using Gemini as this reward model. So to walk you through what that looks like, we have our initial SIMA 2 agent. Again, it's getting around this kind of like 15, 20 point score on average. And then over successive rounds of going through that loop, that self-improvement loop, we can actually get that agent up toward human level performance. So you can break that down by different task. So each task here is each point on the x-axis is a separate task, and we're sorting them by performance level. And so you see the initial agent is okay at some of these tasks, but quite poor at most of them. And then with successive rounds of fine-tuning, data collection, you can get up toward human level performance across the vast majority of tasks. So just to kind of walk through where those videos are, you're starting out with maybe very poor performance on a particular task. Eventually you get toward reasonable performance where you're succeeding, but not as efficiently as possible. And then eventually you're just kind of doing this very automatically. So that was self-improvement on a fixed set of tasks where we had humans supplying this database of tasks, but we'd like to be able to move beyond this pretty constrained setting towards something more flexible. So what we explored next was an expanding set of tasks. So you actually have yet another instance of Gemini, which is serving as your task setter, and that's providing instructions based on the current observation to the SIMA2 agent to instruct it, try this task right now. So you can collect much more varied data, a whole lot of different types of tasks, from menu use to object interaction, tool use, things of that sort. And so we have this massive data set that we've collected from deploying these 3 instances of Gemini. And we wanted to see how good is the resulting agent. We don't just have like one particular task we want to care about. We actually want to try to see, can we get this agent through the initial portion of this game? So this is the technology tree for ASCA, for the initial portion of ASCA. And just to kind of walk you through here, so we have some resources that you need to collect. You need to craft some of these particular items, which involves using a new menu. Those unlock additional resources. You can also build buildings to progress through the game. And when we put each of these agents in, we saw different levels of performance. So the SIMA1 agent, for all its flaws, was actually able to collect some of the initial resources that you need. It was able to pick up a stone in a game it had never seen before, but it only got 2 steps in to this technology tree. When we looked at the SIMA2 agent, it was able to collect a stick, it was able to collect some flax, but it wasn't able to progress further. It wasn't able to use the menu to actually get through the game. Versus when we put this SIMA2 self-improved agent in, over the course of an hour, we were able to get it to actually build a shelter, which is pretty far through this tech tree. So we think there's definitely something here in which we're seeing this improvement based off of this self-play. And it's really exciting to see that progression with humans kind of only on the periphery providing the occasional prompt. So we've talked about new video game environments, but we also have all these generated environments. And so could we do something similar, for instance, in a Genie environment? So we looked at actually divvying up our environments into 2 sets. We have things that are kind of urban environments, like you're on a sidewalk or you're in a store, or a natural environment where you're out in nature, you're under the water, things like that. So what we saw was on the train tasks where you're actually running the self-improvement loop in a Genie environment, you see between the initial checkpoint and final checkpoint a pretty reasonable improvement over most of these tasks. So you might, for instance, start with this task like find a lollipop, and you're just kind of looking around this candy store. You've never trained in this environment before. You don't know exactly where to look. Versus the self-improved agent kind of looks around initially, sees these lollipops in the distance, walks over, and looks at them and stops. So it's learned this new task in this Genie environment. But what was even more kind of surprising was that you can take that self-improved agent that's only trained in photorealistic urban settings, put it in a photorealistic natural setting, and you see a similar amount of improvement, albeit not uniformly, but you do still see quite a bit of improvement. So it's learned some general purpose navigational skills here, where you say, walk over to the single red mushroom. The initial agent latches onto a yellow mushroom or these gray mushrooms. It's getting kind of distracted by these different visual cues, versus the self-improved agent walks right over to this red mushroom and starts to just focus in on that. So it's pretty impressive to see that actually training in a subset of environments provides generalization and that improvement to a whole other set of environments in all these photorealistic settings. And this kind of suggests this pipeline through which you can get better video data, more and better video data, yielding better world models, and using that as a training ground to train better embodied agents. So it's a really interesting direction for future research there. Okay, so what I've shown you is SIMA 2. It's a more capable agent as compared with SIMA 1. It's more general. It can perform pretty complex tasks in environments it's never seen before. And we've demonstrated this self-improvement loop whereby we can use additional instances of Gemini to bootstrap from an initially fairly capable agent to a much better agent through self-play. So I wanted to take a few minutes at the end of this talk to just talk through what are the open problems. We've shown this improvement. We have a pretty capable agent, but I still think there's a lot left to be figured out that ripe grounds for research. One thing in particular is this notion of like a universal reward model, or reward models generally. This is a point that our collaborator Jeff Clune really got me hooked on. And it's this thought that we have in this self-improvement setup this Gemini model where you can prompt it to provide different scoring criteria. You can provide it a goal, a trajectory, and it'll give you a score. Maybe it'll give you some report on how you did. It's like this critic. But it requires alignment with human preferences. It doesn't improve with additional experience. And we're really dependent on language for goal specification. So I think we're still missing some kind of method of deriving a general purpose mapping from goals and trajectories to some form of feedback signal to the agent. And I think just reward models and reward generally is just such an understudied problem that we really need more progress here if we, in this area in particular, if we want better embodied agents. Another area, probably clear to everyone, is a notion of continual learning and adaptation. So the SIMA 2 agent, when you put it in an environment, it really doesn't do any improvement within that interaction. So there's no parameter learning during that interaction. It doesn't leverage the context in any clear way for like an online self-improvement. And that's just something that an agent really needs to be able to do if you want to learn rapidly from self-generated experience. And we need to be able to do that as well without without interfering with the existing capabilities of the agent. Another area that's we really have not fully figured out is long horizon control, being able to take, right now we're instructing the agent with these sub goals, but being able to put the agent in with a long horizon instruction and have it figure out its own sub goals along the way to reach that overall goal. We're currently operating over the span of like minutes, and we're not really able to break long horizon tasks into these shorter tasks reliably. It's somewhat solved with, I saw the task setter. It's somewhat solved by composing Gemini with the agent, but I don't think that's necessarily the end-all be-all solution. We need some way of allowing agents to flexibly break down tasks of any horizon. And we can build better harnesses around the agent, but I'm not sure that's necessarily the end solution to this problem. And then open-ended learning. So we talked about having that task setter, but it has no notion of real curiosity or learning along the way. It's not seeking out novelty or satisfying some curiosity, and it's not really learning from that online interaction. So we need agents that can, effectively explore a novel environment, figure out all of the affordances, everything you can do, much in the way humans are able to just find every single possible state within an environment, every possible affordance. And I think a lot of these different aspects are getting at this overall question of like, we've shown that you can train an agent, you can then deploy that agent and instruct it, and it can do a lot of things, but it's not really an autonomous agent. We really would like to be able to have agents where you can semi-autonomously just deploy them in a new environment, and they can learn all of the different affordances in that environment and learn to control those aspects of the environment. So we're really still scratching the surface when it comes to this overall notion of like an autonomous agent. And I think there's a lot more work to be done in that direction. Okay, so this is work that's presented on behalf of a much broader team. A lot of fabulous people worked on this. And we have a blog, which is shown here, as well as a tech report that came out in, I believe, early December. So I encourage you to check out both of those, and feel free to ask questions or follow up offline if you have, or online if you have additional questions. Thanks.